Hello, grade 9s. We are going to talk about 2.4 exponent law, specifically when dividing today. So yesterday's class, we did an activity where we tried to figure out a rule that always seemed to work when we divided one power by another power. Now, both of those powers had to have the same base for this to work, and we showed it using repeated multiplication. We did a whole bunch of different things, but do you remember that rule? What do we get when we simplify two powers through division with the same base? We end up subtracting those exponents, okay? So if I have x to the power of m, which is just a representation of what could be at the top, divided by x to the power of n, noticing they have the same base, I simply end up with the exact same base, but subtract the top exponent by the bottom exponent. Okay? Now, of course, x, m, and n are all just placeholders for numbers, right? So, a couple of things that we want to point out here. This exponent law, this exponent rule is just a shortcut. It's a way for me to simplify a little bit more quickly. But if I ever forget that exponent law, I could always resort back to repeated multiplication and to help me get there, right? If I wrote this out as repeated multiplication, I could cancel out that base at the top and the bottom when I see it repeating and simplify it. Instead of saying like x over x or 5 over 5, I could cancel them out to be simply just ones, okay? But an exponent law is a way to shortcut there. So here I notice I'm subtracting my exponents. Something else that I notice is that this is when I only have division of powers. So my last law, or the last law we talked about, was when we had the multiplication of powers. This exponent law works for the division of powers. So this is also true if I had it written in a different way that still implied division. So I had x to the power of m, and I wrote my division horizontally instead of in the form of a fraction. It would still work. That fractional format just helps us see the cancellations a little bit better. And lastly, I'm noticing that this law only works, what we discussed last time, is if the bases are the same. So the same base. Now, this exponent law, like all other exponent laws, are just a shortcut for the long written out version of things. So just to give us not to give us an example, we'll look at the first example later. But just really, really, really important is that exponent rules only work if the powers have the same base. If they do not, then that cancellation that we see when we do repeated multiplication doesn't occur. It doesn't take place. So we need to have powers with identical bases for this shortcut to work. Okay, now we're going to take a look at a couple of examples today. And then just like last time, we're going to look at some more deeper thinking based questions to make sure we're on the same track. And that's going to be it. Then the rest of class is going to be used for practice, for the 2.4 practice that will come next. So in these questions, notice the instruction is to simplify. So I want to have my final answer in exponential form with the smallest base. So I want to make sure that I'm expressing my final answer as a single power if possible, or a combination of powers. Whatever I can simplify to is fine. But I'm not evaluating, right? Evaluating means to tell me what that power is equal to in standard form. But simplify is I just want to go from multiple powers to fewer powers than what I started with. So if I start with 2, 1 is obviously what I want to end up with, if possible. But if I start with 5, maybe it's not possible. Maybe they don't all have the same base to simplify to 1. So I'm just going to end up with fewer powers than before. Okay, for this first example, I am going to get us to write it as repeated multiplication, just so that we're all super clear on how that canceling out happens. So I am going to rewrite 2 to the power of 6 is 2 times 2. Okay, try that again. 2 times 2 times 2 times 2 times 2 times 2. So 6 2's all multiplying together. Divided by 2 to the power of 4. So 2 times 2 times 2 times 2. Now this is why we can always backtrack and always rely on repeated multiplication to help us. Because just like any fraction, if I have a numerator that is identical to a denominator, so in this case, a pair, a 2 at the top and a 2 at the bottom, I can reduce this fraction to be equal to 1. And I could do the same thing with the next pair of 2's. And the next one and the next one. Now, you can just draw a line through it because that's the easiest way to represent it. But I do get 2 to the power of 2, which is my final answer. It is a simplified version I am looking for here. Of course, with that exponent law in hand, we will not have to write things out as repeated multiplication. But I cannot stress enough how great repeated multiplication is if I am ever stuck and I forget that exponent law. Excuse me. Okay, we're going to do the rest using the exponent laws. I actually would love if you could pause the video, try example B, C, and D, and then reconvene in a few minutes. Pause. Okay, we're back. Unpause. So in the next one, when I take a look at this, these powers x to the 13 divided by x to the 5 have an identical base. Because it is division of powers with the same base, I can subtract my exponents. 13 minus 5 gives me x, the same base, to the power of my new exponent of 8. Okay, looking at C. I off the bat can see that I have some powers with identical bases, but I also notice that I have some numbers there and they don't currently have the same base. Now, if it is possible, I'm always going to see if I could turn my numbers into powers of the same base, because then I would be able to use my exponent laws here. It is not always possible, but sometimes it is. Now, you might be thinking, ooh, 27, that's one of the ones that I know. Something that popped out to me. Perhaps you know what 27 is as a power. If I didn't know, though, I can always resort to a factor tree, right? 27 is 9 times 3. 3 is prime. 9 breaks down to 3 times 3. Both of those 3's are prime. So 27 is the equivalent of 3 to the power of 3. So on my first line here, I'm actually not going to do any exponent laws, but I'm simply going to rewrite 27 as 3 to the power of 3. Now, if you recall from our rational numbers unit, we had to bring down every single step of work, even if we didn't do anything to those numbers. We need to keep that same process, that same necessity of bringing things down, even if we're not actively doing anything to it. So everything else continues. Now that I'm in a place where I have powers with the matching base, I can go ahead with my exponent laws. So when I do this, I get 3 to the power of 4, and that is, of course, being multiplied by a to the power of 9. Okay, last one. Let's crush it. Here I've got D. I've got a bunch of different powers, and I see a bunch of different matching bases. I'm pretty stoked about it. Life is pretty good. So when I do that, something that may or may not help me, just a reminder that exponents apply to what's directly next to it. So this 2 that I've just circled here only applies to the A, which means the exponent on the 2 at the bottom here is just a secret 1. Now, in the past, I found that some people find it useful for us to go ahead and write that in there. It's not always something that we need to do, but if that's going to help us visualize it, perfect, include it in. The only time we are not including an exponent of 1 is in that final answer. Okay. As I do this, my exponent laws, I am subtracting my exponents, top from bottom. So I end up with 2 to the power of 5 minus 1, which is 4. I have a to the power of 5 minus 2, which is 3. And b to the power of 3 minus 2, which is 1. Now, I just wrote the 1 in there, but I do not want to include it in my final answer because that ends up being a communication error, specifically a final answer E4 error. So this is what I get when I'm all done here. I am going to kind of briefly remind us of an example we saw yesterday. I don't totally remember all the little details, but I think it was something along the lines of 10 x to the 4, or maybe it was, I don't know, x to the 7. I'm going to say y to the 4 divided by 5 x to the 3. I don't know. I'm making something up, but it's similar to the one we saw in the activity at the very, very end. Maybe you got to it, maybe you didn't. Okay. Now, in this case, I have some powers with the same base, right? I have the y's, both powers with the same base. I have the x's, both powers with the same base. The numbers are not. And there's nothing I can write 10 as or 5 as to be powers with the same base. Now, yesterday I went group to group, but I just really want to stress this, is that my exponent laws, like we said, only work for powers of the same base. And because 10 and 5 cannot be written as powers with the same base, we are not using an exponent law on them, right? So instead, we are going to perform division like we normally would. 10 divided by 5 has always been 2. So we are going to maintain that as an answer of 2. We're going to continue with everything else. We get x to the 7 minus 3, which is 4, and y to the 4 minus 2, which is 2. Now just hear me out for a moment. What if my numbers weren't 10 and 5, and they didn't divide nicely? Let's see. What if my numbers, it changed the question, was, 10 and 16, right? I can't divide 10 by 16 and end up with a really nice number. We know that. But just like before in our last unit, we can look at 10 over 16 and think, I could simplify that, right? Top and bottom, both divisible by 2. So just like before, even when things didn't divide nicely, we could see if we could simplify them. We are going to continue to simplify them. So 10 and 16 to both divisible by 2. The 10 would turn into a 5. The 16 would turn into an 8. So my final simplified number form would be 5 over 8. It is okay to have fractions in this unit. It is okay to have a denominator even after I've simplified. Simplified just means to condense any possible powers into fewer powers and to condense any possible numbers into fewer or simplified versions of that number. Okay? So I just wanted to point out what happens if those numbers couldn't be turned into the same base, just to remind us that division or simplification of fractions is always going to still be an option. Okay. Thank you for bearing with me on my tangent. All right, now these last two examples, you'll probably look at them, you'll read them, and you'll think, hey, aren't these very, very similar to the two examples that we looked at in the 2.3 notes, except the 2.3 notes had to do with multiplication, and now we're doing the division of powers? And if you said that, I'd be like, yeah, way to recognize the pattern. So in this case, we're looking at a question that says, use repeated multiplication to show how we know that a to the power of 13 divided by a to the power of 6 is equal to a to the power of 7. And remember, when we saw the word show how we know, we also said sometimes we could see the word verify as another way that exists. Or we could say justify that blank is true or blank is false, right? Those are just ways for us to indicate how we know something works without using that shortcut strategy. And one of the things that we said, how we would represent that properly in math, is that we would cut that equation into half. And when I say half, I don't necessarily mean 2 equal halves, but I do mean that we're going to cut it at the equal sign. And when we do that, we're going to end up with the left-hand side of the equation, whatever's on the left-hand side of the equal sign, which is a to the power of 13 divided by a to the power of 6. And we're going to split it into the right-hand side, which in this case is just simply a to the power of 7. And remember, the goal here was to get both sides into a format where they looked identical, because we want to show that that statement is true. So we want to get it to a point where both the left-hand side and the right-hand side are identical. Because if they end up being identical, then I could end up saying the statement is in fact true. Now, repeated multiplication is the skill here. It says so in the question, but really anytime we're trying to show something in exponent laws, repeated multiplication is always going to be the way to go. Always, 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 forever and ever. Amen. Okay, now, if we're doing things in repeated multiplication with division, it's always easier to see the cancel outs if I write it as a fraction instead of horizontal division. So my first step on this left-hand side is actually just going to be to rewrite it as a fraction rather than to write it as horizontal division. And now my goal again is remember to use repeated multiplication. So let's do it. A to the 13, that's A. And I'm just writing all of them out to get 13. And I'm double counting because sometimes I get carried away. And then I'm, of course, writing that denominator as well. Much fewer A's down here. While I'm in the mood of repeated multiplication, I might as well also do same kind of strategy with my right-hand side. The right-hand side is much more simplistic because it's a simple 1 power. And so we're going to write that out as a to the power of 7. So 7 A's all multiplying with each other. Okay, now we've done the repeated multiplication, but my two sides do not look equal quite yet. But we talked about if I have the same thing in the numerator and the denominator, because it's just a multiplication statement, right? All my A's at the top and all my A's at the bottom are multiplying. Remember, in fractions, we can reduce when I have multiplication. So an A at the top will reduce with an A at the bottom. They will cancel each other out. They will turn into ones. And I could do that for 6 of my A's, leaving me on the left-hand side with 7 A's in my numerator all multiplying together. Now at this point, I am done the math. How I know I am done the math is because my left-hand side, what I've written there, looks identical to what I have on the right-hand side. And what I mean by looks identical is if I said, okay, someone, quick, go to the other room. And I switched places of what I wrote on the left-hand side and the right-hand side, what I've highlighted, you wouldn't be able to tell the difference. I mean, maybe attention to detail, you have font notices, and you're like, this day is a little bit more squiggly than the other. Okay, fine, whatever. But the point is that they look or they mean the exact same thing. You can't tell me they're different. Now remember that whenever we're verifying, showing how we know, justifying that something is true, we can't just show the math work and be like, we're done. We need to have a conclusion. And remember, what makes a good conclusion is that it includes 2 parts. What do we see in the math? And what does that tell us? So, what do we see? We can see that we've turned the left-hand side to be equal to the right-hand side. We see that those two things are the same. So I'm going to write that. I'm going to say, since the left-hand side is equal to the right-hand side. Okay, what does that tell us? Well, we wanted to say that the original a to the power of 13 divided by a to the power of 6 is equal to a to the power of 7. So that tells us, so since the left-hand side is equal to the right side, that tells us that a to the power of 13 divided by a to the power of 6 equals a to the power of 7 is true. Now, of course, this is written in a way that perhaps might not actually connect with you. Maybe that's not your language, right? You are welcome to say, I see in my work the left-hand side is equal to the right-hand side. That tells us that the statement a to the 13 divided by a to the power of 6 is equal to a to the 7 is true. You can literally phrase it as, this is what I see, this is what it tells me. That is totally acceptable, totally fine. What we've written is just kind of a slightly shortened version of that, a little bit more concise, but it gives us the same information. We said what we saw and what that meant. Okay, last but not least, I want to create possible values of A and B that would make the statement true. Okay? Give it a try. Give it a go. See what you got. Pause the video. And welcome back. Okay, so remember, just like last time, there are multiple possible answers that could make the statement true. Realistically, I just need to make sure that my A value, when subtracted by my B value, will equal 5. Now, again, tons of possible options, but the importance that I want to talk about today is how to represent your answer, right? We said I want to state a value of A and B, which means I need to have somewhere that A is equal to blah and B is equal to blah, right? I can't just say 12 and 7 because the order really matters. If A was 12 and B was 7, yeah, that works because 12 minus 7 is 5. But if I had A as 7 and B as 12, I'm getting a -5. That's not working. Now, of course, other answers are possible, right? I can have A is 10 and B is 5. I can have A is 6 and B is 1, right? Doesn't quite matter the exact answer that you get, as long as when I take my A number and subtract my B number, I end up with the number 5. Okay, that's it. That's all. Those are the notes. There are some practice that follows. Please complete the practice, and I will see you when I see you. Adios, muchachos.